Good. Out of Despicable Me, and this is how you remember Vector.
We were just talking about this yesterday.
Yeah, we were.
Yeah, I remember.
Hey. I'm applying for a new villain loan. Go by the name of Vector. And it's a mathematical term, a quantity represented by an arrow with both direction and magnitude. Vector! That's me, as I'm committing crimes with both direction and magnitude. Oh yeah!
So help me, you do that on the test when I ask you what a vector quantity is, I will kick you out of my class. So, but, no, you will not get your extra credit. That will so not get your extra credit. So, okay, now back to our story.
It is very amazing what you can find on YouTube.
So what we got today is a lab, and then we'll go over the assignment, do the lab, and we'll probably take my name in vain by the end of the day, but that's okay, we'll talk about that later. Okay, it's true. All right, any questions on the assignment? Sydney?
Yeah. On number 6, Mary Bobbins bullet,
Says could, now, notice I didn't say find the area, okay? I said, could you find the area under the curve to determine the displacement? I didn't say find it, I said, could you? Yes, read.
So along with that, like the fourth dot down says find displacement. Since you can only do that on velocity ones, do you just subtract like the tallest point starting point?
Okay, now let's talk about that last dot. Could you find the area under the curve to determine the displacement? Well, look. You've got this, which is position, and this is going to be in time, okay? And when you get done, it should look something like this, okay? That's what your position time graph should look like. So you got a pot, and you're starting here at 250. You're going to go up, and then you come back down, right? So these units here are in meters. These units here are in seconds. So if you were to find the area, okay, just based upon the units, what would you multiply together to find the area? What two quantities would you multiply together? Don't make this difficult. Sydney, question. So, what's this measured in?
Meters.
This is measured in?
Seconds.
If you multiply meters times seconds to find an area, what are you going to get?
Meters per second.
No, you're not going to get meters over seconds. Let's just say I'm going to take 100 meters times 5 seconds. What do you get? You get 500? Then what units? You get meter seconds. Is that what displacement is measured in? No. What units is displacement measured in? Meters. The area underneath the position time graph gets you butkus. It has absolutely no meaning whatsoever. Okay? You can find it. Good luck. It won't tell you anything because units don't work out. Now, if it was a velocity time graph, and it's not, but if it was a velocity time graph, and I would multiply meters per second times seconds, then what would I get? Then I'd get meters. Okay? But that only works on velocity time graphs, not on position time graphs, because the units don't have any meaning. Okay? Because just because you can find an area doesn't mean that it means anything. Okay? Garrett?
Speaker,
It is a little annoying, isn't it?
a little bit.
Kind of like this low hum of a freshman in the room. Okay. Now, a couple of things. On number 7, when you're talking about how far a beam of light would travel in a year, otherwise known as light year, that should obviously be a pretty big number. And that answer, if you do it right on number 7, should be something times 10 to the 15th meters. Okay? If all goes well, that should be something times 10 to the 15th. Now, the nearest star, anybody know the name of the nearest star to the Earth?
Is
Star!
is it Centauri?
Yeah, Proxima Centauri.
Yeah.
Okay? Proxima Centauri. Okay? Okay, beyond that one. But yeah, beyond the big ball of gas that's in our neighborhood. So, and that's about a little bit less than 3 light years away. So even if you could travel at the speed of light, it's still going to take you about a little bit less than 3 years, even if you could travel that fast to get to that star. And now here's the weird thing, and don't think about this too much, okay, or you will do drugs. So when you look up at the night sky, you're actually looking back in time. Because even if, let's say, for example, on August 28, 2014, let's say Proxima Centauri goes supernova and it explodes, okay? We won't get that news for about 3 years, because even that light traveling at the speed of light is going to take about 3 years to get here. So when you're looking at stars that might be, 10, 100, 50,000, 100,000 light years away, by the time that light gets to us, you are looking back in time, because of the fact that that light has been traveling so far to get here. So, let's say, for example, your birthday is today. So if you had a star that was like 18 light years away, right, then if light was emitted on the day you were born, that light would just be getting to that star that's 18 light years away. So it gets a little bit weird if you think about it. So, as I said, don't think about it too much. Okay, now, let's talk about number 10, okay? Because and 10 and 11 kind of go hand in hand. And I just want to make sure that you have somewhat of a reasonable answer, because sometimes I get some really jacked up answers on number 10. So I want to know, how long would it take the sound of thunder to travel 1.609 kilometers, which is equivalent to 1 mile, traveling at a velocity of about 330 meters per second? So here's the deal. So first off, what are you going to have to do with the 1.609 kilometers? Change it to meters by doing what? Multiply by 1,000, right? So here's the lightning strike, okay? It's about 1,600 meters away, and it's going to travel in round numbers about 330 meters per second, and you're standing here, okay? Right? And we want to know roughly how long it's going to take. So right away is the time that it's going to take for that thunder to get to you. Just looking at this, without doing any calculations, okay, without doing any calculations, is it going to take more than a second or less than a second to get there? Why, Riley?
It's only 300 meters per second and way more than 300 total length.
Yeah, so if you just look at this and go, well, even if I was 330 meters away, it would take exactly 1 second. And I'm certainly more than 330 meters away, so I know my answer to this question has to be more than 1 second. Because of the fact, just because I'm more than 330 meters away. So if you look at that answer on number 10, and if your answer is less than a second, something has gone horribly wrong. Now, and this always baffles me, and I don't know why you all want to do this. But yesterday we said that distance traveled is equal to velocity times time, right? And for whatever reason, and I don't know why, but this is the most common, literally the most common mistake that's made in this whole unit. As a year ago, oh, time is velocity divided by distance. Okay, this is what you're going to try and do. You're going to take velocity and divide it by distance. Well, here's what's wrong, and I actually gave you purposely one of these on that first dimensional analysis sheet. If you take velocity in meters per second and you divide it by a distance in meters, do you get seconds out of it? No, because if you take meters per second and multiply it by the inverse of meters, you get units of 1/seconds. Now, you can wish that this is seconds all you want, okay? Call your fairy godmother whatever you want. This is not going to turn into seconds, okay? No matter how much fairy dust you sprinkle on this thing, it is still going to be 1/seconds. But for whatever reason, you all want to think that, oh, velocity divided by distance is time, and it's not. So, just keep that in mind. Make sure on number 13 that you have indicated when it is speeding up and when it is slowing down with arrows. Don't make me guess. All right, we're good? Anything else? Life is grand. Get that handed in. So, shut that down. This kind of compilation of this whole idea of position time graphs and velocity time graphs, and see if we actually understand what's going to happen. So, though I want to do a couple of like pre-lab activities, kind of make sure everybody's on the same page. So, what I'm going to do is I'm going to take this fancy dancy red cart, right? And I'm going to give it a push, and I want you to observe what's going to happen. And the only thing I want you to do, okay, is draw the velocity time graph and the position time graph. It's just a sketch, okay? You're not going to hand it in, okay? So I want you to observe what it's going to do. And this is going to be 0. Positive positions going that way, so it's going to have positive velocity, okay? So then once we kind of get what's going to happen, we'll draw it up on the board, and we'll see what's going to happen. Okay, you ready? Sydney, we're ready? Okay. So all I'm going to do is I'm just going to give it a little bit of a push. And again, do not include the push. Okay? Do not include the push. We're going to start this analysis from the very instant that I let go of this. And wherever I let go of it, that's going to be the initial position. So I'm just going to give this a little bit of a push. Simple. Position time graph, velocity time graph. So, if somebody thinks they have, or if somebody just wants to tell me what you think you have, let me know. Or you can draw it up on the magic board. Captain America, what do you got?
For the position time graph,
Yeah?
let me go up there and draw it.
Yeah.
Okay.
Okay. Anybody else? What about the velocity time graph? Rosie? Or Reed?
I'll wait.
You're waiting? Okay, nice. We good? What's wrong? What about it?
Not starting at the reference point.
Yeah, because we said Captain America has the right shape, but we said wherever that point where we start, that's going to be the reference point. So you have the right idea. We're just going to shift it down a little bit. Now, did you mean for this to be like a straight line and then it levels off.
Yeah, because well, it's like slowing down and then it just stops.
Yeah. But what you have looks like it rolls at a constant velocity and then it just stops.
It's kind of like a curve, a little bit of a curve.
A little bit more like that action.
Yeah.
Okay? Everybody cool with that?
That's cool.
That's cool. Does this show it slowing down, Rosie? Why? Really? Velocity is increasing over time. Decreasing over time. Big difference.
That's what I said.
Okay. I thought, okay. So,
I thought
you're going
decreasing
to
was
start
the
with
word.
some positive velocity. What's the sign of your acceleration? Really? Negative. Cindy's over there going, negative, negative. Okay. Negative, Ghost Rider. Okay. So, because if something's going to slow down, what do you have to have in terms of velocity and acceleration? Same sign or opposite sign? Opposite sign. Okay? Right? So, these two curves are compatible. This shows it slowing down. The position time graph shows it slowing down because the curve is becoming more gradual. Okay? Good so far. Now, we're going to change it up a little bit. Now, Graver, I need you to stop this. Okay, I'm going to push it at a 5 speed. Yeah, just move that. So I'm going to push it to you, right? And a little bit faster than what it was before, and then I want you to stop it. Okay, like just grab it and stop it. You ready? Okay. Bingo. I want the position time graph and the velocity time graph for that. Well done. So this is rolling. And this is stopping quickly. Paige, got something?
Yeah.
Huh? Come on. Step away from the Starbucks.
Okay, now I have to think of what I did.
Okay? So do you want it to be speeding up?
Like it's, yeah, kind of. I mean, you're pushing it.
Don't include the push.
Well, I know, but like it's me. Gosh, Dave.
I can live with that. Okay. Now, these are right, okay? For the most part, we're going to tweak it a little bit. So, Paige, you drew a straight sloping line which would indicate what? Okay, accelerating at a constant speed. Those two concepts are completely...
I know.
Yeah, it's like, I'm going to drink, but I'm sober. No, okay? It won't happen. You're either accelerating or you have a constant speed, or technically velocity, okay? So, as it rolled, do you think it stayed at a constant speed, or do you think maybe it slowed down a little bit? Yeah, it might have slowed down a little bit, okay? It certainly couldn't go any faster, because as soon as I let go of it, friction's going to start to work against it. Friction isn't very much of a force when you have rolling wheels, okay? Right? So, if anything, we could have done just a little bit of a tweak to it, maybe put just a little bit of a curve to it, but then very abruptly it's going to stop. Now, that's what kind of Reed had going on here. He had it rolling along at a pretty much constant velocity, and then all of a sudden, bam, it stopped. Okay? So I'm going to put just a little bit of a tweak to reads, not much, just a little bit, to indicate that it's going to slow down just a little bit. Okay? Then it's going to stop. Now, look at this. In both situations, what's the final velocity of the cart? 0. What's the difference between the two of them? Yeah, the rate at which it goes to 0. This one, we let it roll for a long time, and it would eventually stop. This one, it was rolling, bam, made it stop very quickly. In both situations, is there acceleration? Hayden?
Yes. Or, yeah,
Yeah, in both situations, there's negative acceleration, right? But which one clearly has the bigger acceleration? When Graber stopped it, or when I just let it roll and it stopped?
When she stopped it.
When she stopped it, right? Because remember, if you're just given two velocity time graphs like this, how could you figure out which one had the largest acceleration? Just looking at the graph, how could you determine which one had the larger acceleration?
Whichever one has a steeper slope.
Whichever one has a steeper slope, right? Because the steeper the slope, the bigger the acceleration, which means your velocity is changing more quickly in a given amount of time. Okay? Got that one. Wonderful. Now, Graber, we're going to do this again. But this time, we're going to change it up. This time, I'm going to push it to you. You're going to stop it, and then you're going to push it back to me. Okay? And again, I want a position time graph and a velocity time graph. We'll try to do it a little smoother. Okay? So, and again, do not include the push. Okay? Now, you need to include her stopping and pushing it back to me, but don't include my push. Okay, you ready?
We include your stopping.
No, don't include my stopping. I'm not a part of this. This is all about Graber. Going towards her, she stops it, she pushes it back. Now, Garrett, turn that around so that pretty clear people can see what we're doing. Okay, we'll do this one more time. Okay? So I'm going to do the push. She's going to stop it. She gets pushed back. Okay? So the position time graph and velocity time graph. Now, fundamentally, what has changed between this situation and the first two? What's the biggest difference? What do you say?
Direction.
There's a change in direction. Okay? Now we have a change in direction that we didn't have before. So, position time, velocity time. Now, on this velocity time graph, I've given you 0 meters per second. Okay? Here's position, here's 0, boom. Get it? You got it? Try it. Come on. I got faith in you. Anybody that's wearing an Atari shirt, I got to have faith. Nice. Well done. So I got the position time graph. Rosie's going to step up for the velocity time graph, or a different version of the position time? Velocity time.
Serious thinking.
Serious.
Yeah. There you go.
Okay. Okay.
You said, imagine like you didn't stop it at the very end.
Yeah.
Okay. So
Now, the top half of Rosie's graph is spot on perfect. Okay, it is literally perfect. Okay? Because she's showing it starting with a positive velocity and then slowing down and then stopping very quickly, which is what happens, and that matches perfectly with what Garrett drew. Okay? Garrett had a little bit of a, this thing curving upward, indicating that it's slowing down, and then very quickly it came to a stop, okay, when Graber had a hold of it, and then pushed it back, shows a change. Now, if that's what this is showing, this might be a little bit steep, but it's not bad, okay, because it probably didn't slow down a whole lot as it was rolling, but the most important thing is that very quickly it was stopped. Now, I'm going to look at what Rosie drew. Now, pretend that all you see is the bottom part. Okay? That's all you see is the bottom part. Okay? Don't worry about the top. The only thing you can see is this part. If all you saw was going from here to here, what would you think it was doing? Speeding up or slowing down? Why?
So not both negative acceleration and negative velocity.
Perfect, right? You have negative acceleration, I have negative velocity, it looks like it's speeding up. Okay, and it does, because clearly it does have to speed up, right? Because Graber's going to push it in the opposite direction. So, that part's good, okay? Right? Because this is when Graber is pushing it, and it's speeding up. Now, as it rolls, what's it going to do? Slow down very much? No. So here's what we do. I'm going to tweak this just a little bit. Okay? I'm going to tweak it just a little bit. So I'm going to put a little bit of a horizontal line here because that's when Graber had it stopped. Okay? Now, if you just look at her pushing it and me rolling it and rolling back to me, Graber, did it take you very long to push that cart back? No, you just kind of went, right? Just gave it a little bit of a push. So how could you show a very quick gain in negative velocity? What would this line do to show a very quick speed up with negative velocity? Well, it's either going to go up or it's going to go down. Going to go down, right? Okay? Now at this point, she's going to let go of it. She's going to let go of that cart at this point. So what's it going to begin to do? How are you going to show it slowing down? Now, like this, Riley?
Yeah.
No. No? Because look, when is it going fastest? On that return trip, when is it going fastest? As soon as it leaves her hand. Okay? As soon as it leaves her hand, that's as fast as that dog is going to run. Okay? Because as soon as it leaves her hand, it's going to begin to do what? So how are you going to show this slowing down with negative velocity? It's either going to go towards zero or it's going to go away from zero.
Away from zero.
Away from zero is going to slow it down.
I mean, we don't include the stopping. If we include stopping, then we would do that a little bit.
Well, I know, but here's the point. Even as it's just rolling, easy for me to say. Even as it's just rolling, is it going to slow down a little bit? Yeah. So I'm going to have some action like this. Okay? So look at what this is showing. It started with a big positive velocity. It's rolling along, slowing down. Boom! Graber stops it. Okay? And we slow down. So we're slowing down, right? And now we're stopped for just a second because she's debating, ooh, do I push it back or not? Okay, I'll push it back. Now, from here to here, is it speeding up or slowing down? Speeding up. How do you know?
Negative acceleration, negative velocity.
Negative acceleration, negative velocity. So here it's going to speed up. What's it going to do here? Slow down because now I have positive acceleration with, and I'm going to slow down. So what's the only time in that trip it speeds up? When she pushes it back. Okay? Got that. Now, we're gonna do one other tweak to this, okay? We're gonna do one other tweak. So, Graver, we're gonna do this again. Now, with this one, I just want you to have your hand out, okay? And it's gonna act like a bumper, and you're just put it up there on that seam so it doesn't go like, so it stays on this side of the table. Okay? So we're gonna do the same thing, but now we're gonna use the plunger. Okay? Ready? Okay? Now, let's do this again, and I'm gonna do a little faster so it makes it all the way back to me. You ready? Beautiful. What's that velocity time? Now, what's it? Will both graphs still have approximately the same shape?
Yeah,
Yeah? Why, Paige?
because it's practically doing the same thing.
It's practically doing the same thing. What's the only thing we're changing?
No
Is
speeding
that
up.
you're not forced.
Well, I mean, there's no
Stopping.
speeding up or turning
Stop
back.
time.
You're not
Yeah, you can't.
grabbing it.
You're
to
not
stop
stopping time.
Does it
Makes
just
it stop what?
speed up in second?
No.
You don't stop it completely and because it
Does it never stop completely?
does.
It has to stop.
There's just
Why does it have to stop?
Changing direction.
There's three things that have to happen to change the direction. What are those three things?
Slow down.
Stop, and
The wall.
Back up.
so is all that happening when this plunger is in contact with Graver's hand? Yes, because think about this. The plunger hits her hand and it begins to do what?
Back up.
Slow down. No, when it hits her hand,
It slows down.
it slows down because the spring is compressing, right?
Yes.
When is it going to stop? Well, when the spring is fully compressed, right? So, if that spring is fully compressed, then as soon as that happens, what's going to make that cart speed back up?
The spring.
Expanding, right?
Expanding the spring.
Yes. So, compressing the spring is going to make it slow down. Expanding the spring is going to make it speed up. Now, this is a classic example. There's certain things that nature hates. Okay, everyone says, "Oh, nature hates a vacuum," or actually, the technical term if the saying is, "Nature abhors a vacuum." Okay. More importantly, nature hates potential energy. Okay, it really does. And we'll study energy later. Nature hates potential energy. And here's the classic example. If I compress this spring and I let go of it, every time, what's going to happen? It's going to move, right? Nature doesn't like that spring being compressed. It goes, not worth the effort. It isn't like I let go of it and nature thinks for a second, goes, gee, do I expand the spring or not? That's a tough one. Okay, I'll go ahead and push the spring. Okay? If I drop this, every time, what's going to happen?
It's gonna fall.
It's going to fall. Nature hates potential energy. Okay? It does. And if you think about this, nature hates potential energy. Nature likes things that move. So when you compress this spring, okay, and nature goes, ooh, not digging it, oh, I'm going to make you move. Okay? And then it starts to move because it doesn't like potential energy. So when you look at this graph, basically the only thing that's going to happen is that this is going to end up like this. Right? And what's the only thing that's going to happen here? Instead of this part here, where we had the dramatic pause, this is just going to go something like that. Okay? It's the only thing that's going to change. Now, here's what you're going to do in the lab. Working in big groups, okay? You need like probably at least 6 people. Here's what you're going to do. You're going to take the cart on the floor, and here's going to be the wall, and you're going to measure out 1.5 meters, and you're going to put a piece of tape, and you're going to measure another 1.5 meters, and you're going to put down a piece of tape, and when you get done, you're going to take the tape back off the floor. And to make this simple, and we're all on the same page, we're actually going to call this 0 meters. We're going to call this a position of 1.5, and we're going to call the wall a position of 3 meters. Okay? Now, so what you're going to do is that you're going to give it a push, okay, from here, just like I did, and the car's going to roll in, it's going to hit the wall, and it's going to roll back. Now, this is not NASCAR, okay? I do not want you to try and break the sound barrier, you want to put, or try and push it hard enough that you leave like a hole in the wall, bad form. You want this thing to be going just fast enough so that when it hits, bounces back, it clears the wall. Or, excuse me, come back to this point. Now, this is why it takes a whole bunch of people. So, you need one person timing, or you need one person pushing the cart. Now, who's ever pushing the cart, it has to be at full speed before it crosses this first mark. So in other words, I don't want it speeding up past this mark. Just like this, we are not going to include the push. Okay? The push is not included. So we want this thing already traveling at full speed when it crosses this mark. That's how we're going to start this analysis. Now, everybody has to go off the tip of the plunger, because that way everybody's timing the same thing. So, Danny might be timing from 0 to 1.5, okay? So she's going to start when this point crosses the 0, and she's going to stop it when the tip hits 1.5, okay? Now, Daniel might be timing it from 1.5 to 3, okay? So he's going to time from here. Now, he's going to stop it when that plunger is in contact with the wall. Okay? So this is going to be the second interval. Captain America is going to time it from here back. So he's going to time this interval. Okay? Then Cindy might be timing it from 1.5 back to 0. So you need those four. 0 to 1.5. 1.5 to 3, 3 back to 1.5, 1.5 to back to 0. Now, you need somebody else timing the entire event start to finish. So when you get done, these 4 times, when you add them together, should be within 1/10 of a second of the overall time. Okay? So that's the 5th timer. Then you need somebody else timing, or as best they can, just the amount of time when the plunger is in contact with the wall. Okay? So in other words, they're going to start and stop just so that you have somewhat of an idea of how long that plunger is in contact with the wall. Okay? So that's why this is going to take 6 people. 7 if you count the pusher. Okay? But the pusher can also time the entire event. Okay? So you can get by with 6. So you're going to go from here to 1.5, 1.5 to 3, 3 to 1.5, 1.5 back to 0. Okay? Now, stop that. Let me hand out the lab. So, here's the drill. Now, if you have all paid attention, if you look at the pre-launch questions, and I say to do this as a group, we've actually already done this. You can just individually make a quick sketch of these. So, on the pre-launch says, as lab neutral position time graph, velocity time graph for a car being pushed and then stopped quickly. Okay? We've already done that. What did it look like when it's just pushed and then stopped quickly? Yeah, just boom, right? And the position time graph went boom. So all you have to do is make a quick sketch of that on your lab. We already have this. Just make that quick sketch. Then, on number 2, it says draw another set of position time graph and velocity time graphs for a simulation, only this time your lab partner stops the car and pushes it back to you. We already did that. It goes whoop, and then it goes dink, 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 right? Make that sketch. That's all you have to do. Okay? We've already established what those look like. So we kind of did it collectively as a class, the pre-lab questions. Now, on the procedure, you got the 0, 1.5, 3. So here's what you're going to do. You're going to time these individual events. Now, what we need is the velocities in these intervals. So what we're going to assume over a relatively short interval, we're going to assume that the velocity over this interval is constant. In reality, and this is going to be important when you start to draw your velocity time graphs, in reality, that cart is going to be slowing down as it rolls. So what we're going to do is but to get an idea of how fast it's going, we're going to take that timed interval and we're going to take that distance or that displacement and we're going to divide it by the time to get the velocity. So what we're going to do is that it's rolling, to get an idea of the velocity, we're going to use the idea the velocity is going to equal displacement divided by time. Now, pay attention that this is displacement, okay? It is not distance, it is displacement. How can you determine the displacement? What minus what? Final minus initial. So this displacement is going to be position final minus position initial. So look at this. On the way in, where do you start? Where do you end up for this first interval?
1.5.
So you're going to take 1.5 minus 0. Now, in big bold letters, I said, you show me every calculation. There's two calculations that you have to do to get this initial table. The displacement and the velocity. So on that first interval where it says displacement, here's all you have to write down. 1.5 minus 0. That's how far it went. It's not a big deal. Okay? 1.5 minus 0. Then you're going to take that 1.5 meters and you're going to divide it by the time. However much time that took. Then you're going to do the same thing for here. You're going to take this displacement, you're going to divide that by that time. To get the velocity on the way back, you're going to take that displacement divided by that time, you're going to take that displacement divided by that time. Okay? It's all the data that you need. Now, from this, you are going to have to do a tremendous amount of analysis. You're going to have to draw a position time graph. You're going to have to draw a velocity time graph. Now, listen to me. Listen to me very carefully. Here is your guiding light. There's two things to remember. The position time graph and the velocity time graph have to show the exact same thing happening at the same time. So if your position time graph shows that you have positive velocity, your velocity time graph has to have positive velocity. If your position time graph breaks over and that velocity is 0, that's when your velocity time graph has to go to 0. So if your position time graph has negative velocity, your velocity time graph has to have negative velocity. They have to show the same thing happening at the same time. Now, listen to me. On the velocity time graph, here's the second most important thing. On the velocity time graph, you cannot play connect the dots. Okay, listen to me. You cannot play connect the dots. It won't work. You're going to have to extrapolate and figure out, well, gee, when was this thing really moving fastest and when was it slowing down? So the velocity time graph, I'm telling you now, will give you the most fits. But if you think about what we did and what that graph looked like when it hit Graeber's hand and bounced back, that will help you out a tremendous amount. Now, underneath this data table, I've got 3 sets of arrows. On this velocity time graph, there is a tremendous amount of things you have to label. When the plunger hits the wall, when the spring is compressing, when the spring is expanding, when the plunger leaves the wall. Those are 4 distinct points or regions on your velocity time graph. Indicate when the car is slowing down or speeding up using arrows. If it's speeding up, draw an up arrow. If it's slowing down, draw a down arrow. Label the sign of the velocity and the acceleration of each segment. And when I say label, like, I don't mean go to this and go, oh, positive, positive. I have no idea what this means. I have no idea. Now, if you say, oh, it has positive velocity and positive acceleration, or it has positive velocity, negative acceleration, whatever it is, that's cool. But just putting random plus and minus signs has no meaning whatsoever. Sydney?
If you put a key for
That's cool. As long if you put a key and I know exactly what you got going, that's fantastic. Beautiful. Highly recommended. Okay, now, you are more than likely to take my name in vain by the time you're done with this, because it is going to require much thought on your part. Yes, there is a backside with much calculations to do and questions to answer. Okay? All right. You're on your own. 3 groups.
Is that not?
Yeah, shut it down.